Thank you for the introduction. It's nice to be here. Before I begin, I see there's quite a few people online. So if you want to ask questions, you should just unmute yourself and ask. And same with people in the audience, like please just interrupt me and ask questions. All right. So let me start by introducing a kind of question in basic algebra. That is what I want to talk about, and then I'll talk about some of the history, which will rapidly get into topology and geometry, which I think is the subject of this seminar. So here's kind of the first introduction, just to a kind of an algebra problem. So I want to start by fixing some conjugacy classes, C1 through Cn, inside of the special linear group SLRC. Just think some matrices in Jordan normal form. And I want to study the following object, which is the set of solutions to some equations with some constraints. So it'll be x of c. So here C underline is just this tuple conjugacy classes. What is this? This is the set of n tuples of matrices, A1 through AN. It's an SLR C with the n with the following constraint. So first of all, the ith matrix should be in the ith conjugacy class. And then the equation I want to study is that the product of the AI is the identity matrix. So this is some natural equation. We'll see it shows up in a lot of natural settings. So maybe a spoiler is that this will be related to representations of the fundamental group of a sphere with n punctures. Okay, but and maybe right now there's a lot of redundancy. What I want to do is I want to mod out by simultaneous conjugation. So I'll view these things as the same if one tuple can be conjugated to another with the same matrix. So this set has been studied for a long time. So let me give you some examples of things people have been interested in. So first of all, there's the so-called Deligne-Simpson problem. Which is just the question: when is the set X of C not empty? In other words, you fix a bunch of conjugacy classes in the special linear group, or you can do this in other groups too, and you ask, well, can you find matrices AI and CI whose product is the identity? Okay, and this problem was more or less solved by Simpson and Kostov. Many other people have worked on it, but probably Bovy, for example, from a quite different perspective. Okay, so maybe let's suppose we now know when this is not empty. So the second thing you can do is, well, this is an algebraic variety. You can try to compute its dimension. And so the next question is, you can ask when is the set XC, well, you can ask when is it zero dimensional? It turns out if it's zero dimensional, it's actually just a single point. So when is it a single point? So given these conjugacy classes, when is there a unique solution to this equation up to simultaneous conjugacy? Okay, and this is also a famous question. So this is the question of classifying rigid local systems, which I'll talk more about. And it was more or less completely solved by Katz in the late 90s. Okay, so maybe let me actually say a word about Katz's solution, because it will come back later in the talk. So what Katz did is, so given a solution A1 through AN in SLR to the C, SLRC to the N, so an n-tuple of matrices, which is a unique solution to this equation with this constraint, what Katz does is he produces this operation called middle convolution, which produces from this tuple a new tuple of matrices. So A1 prime through AN prime, not in the special linear group of rank R, well, this is rank R minus 1. That's not an SLR, but in SLR prime for some R prime less than R, with the property that it's also a so-called rigid local system. It also corresponds to a singleton set. Okay, and so by iterating this procedure, you eventually get down to the case where the situation where R prime is 1, and it's very easy to solve this equation with 1-by-1 matrices. Okay, so this operation middle convolution reduces any solution to this equation with this property that's sort of unique to a bunch of numbers, and then it turns out that this middle convolution operation is invertible. So ultimately, what Katz shows is that any one of these unique solutions can be produced from just an n-tuple of numbers, which multiplies to the identity. So we'll come back to this. Okay, so in some sense, what I want to talk about is actually older than either of these two questions. So it goes back to the work of Markoff in the 19th century, and then variants of it were studied by Painlevé, Schlesinger, and then more recently Goldman, Eskin, Dubrovin, more others, which is to understand the dynamics of these algebraic varieties. So it turns out these varieties have a huge symmetry group, which I now want to explain. So the goal is to understand the dynamics of some natural group acting on these sets. Okay, so what do I mean by that? So when I say there's a group action on the set, what I mean is that given a solution to this equation satisfying these constraints, I should be able to produce a new one, right? So let me explain how to do that. So let me call sigma I the following map. So given an n-tuple of matrices with multiply to the identity, I'm going to make a new one as follows. Well, what you want to try to do is swap the ith and ith plus first matrix, right? But that's not going to work. That won't preserve this. This equation will no longer be satisfied in general, so you have to fix that up. So what you do is you swap the ith and ith plus first matrix, but then you conjugate the ith plus first by the I. Okay, so what have I done? I've put AI plus 1 in the ith spot, but then I've conjugated it by AI. And I put AI in the I plus first spot. And if you just stare at this for a second, you'll see the product is still the identity. Okay, so this doesn't act on the set, right? Because it permutes the conjugacy classes. I switched the conjugacy class CI with CI plus 1, but an index n factorial subgroup of the group generated by these sigma I. So in other words, maybe let me write this down. So this group sigma 1 through sigma n minus 1, this acts on the set of solutions to our equation with no conjugacy class constraint. On simultaneous conjugation. So an index n factorial subgroup. So which maybe I'll suggestively call Vn. So index n factorial subgroup acts on what I call x of c. Okay, so maybe this notation should be suggestive. This will ultimately be like the pure braid group, pure spherical braid group on n strings. Okay, so I've given you some dynamical system here, some group acting on a set or even an algebraic variety. So what kind of dynamical questions are we going to try to answer? Well, the most basic question you can ask are what are the finite orbits? And I think arguably this question goes back to maybe 1905 with the work of Painlevé. And I'll say a little bit about it, a little bit about the history, but maybe let me just say what the goal of this talk is to give more or less a complete classification. So as a classification, under some mild hypotheses. So for example, so if some Pi has infinite order. In the very special case that Painlevé was interested in, so the case when R is 2. So here we're studying 2-by-2 matrices. Okay. Are there any questions about this? Okay, so let me start the introduction over now. Why am I talking about this in like a geometry and topology seminar? Okay, so let me
Sorry, can I ask a
just of course.
If you replaced SLN by Hermitian matrices, there be a relation with the Horn problem of
Yeah, so the Horn problem is basically the Deligne-Simpson problem or the unitary.
unitary? Okay.
That's right. Yeah, so it absolutely makes sense to it's very interesting to replace this with other groups. Yeah, and I mean the unitary cases. In fact, what we'll see is the unitary case is kind of the case we don't know how to handle. And so but we'll somehow this infinite order case we'll rule that out. Yeah. Okay, so let me now start the introduction over. I want to explain what this means topologically. So where does this problem really come from? So we'll let sigma 0 n be the two sphere minus n points. So maybe let me draw a picture of that. So here's the two sphere. And here I've deleted n points. So pi 1 of sigma 0 n, the fundamental group of this space, you can write as generated by n elements, gamma 1 through gamma n, subject to the relation that the product of the gamma I is guided. So just to draw the picture, here's gamma 1, here's gamma n, and if you go around all of these loops, you get a loop that is contractible by kind of pulling it around the back of the sphere. Okay. So that relation there should look familiar. It's this relation. So what is x of c? So the set x of c we're studying is the set of representations of pi 1 of the true sphere with n points removed, the SLRC, such that rho of the ith loop is in this ith conjugacy class. In other words, it's to say it in a more fancy way, it's local systems on the space with fixed local monotony. Okay, so what is this group action here? Oh, maybe let me make a definition. So the mapping class group mod 0n, the topologist way to define it is to take pi 0, the space of orientation preserving homeomorphism of sigma 0n. So up to finite index, maybe I'll write this wiggly equality to say up to finite index, this is pi 1 of the moduli space of genus 0 Riemann surfaces with n marked points. This is also the pure braid group, pure spherical braid group on n strands. And it's also this group, sigma 1 through sigma n minus 1. Okay, but now it should be clear that there's some kind of dynamical system here. Well, the homeomorphism group acts on of a space acts on that space, right? So in particular, it acts on pi 1 of the space, at least with an outer action. There's some issue with base points. Well, the pi 1 is a discrete object, so that action will factor through pi 0. So, okay, so what we've said is that this mapping class group has an outer action on this group that I got to mod out by conjugacy here, but if you mod out by conjugacy here, which I should have done, I did it over there. Well, that outer action on this group will descend to an honest action on the space of representations up to conjugacy. Okay. So we're studying, we want to study the finite orbits of this very canonical action. And maybe let me just remark, there's kind of a obvious generalization now to a genus G surface with n points removed. Just replace 0 with G everywhere. And if I have time, I'll say something about this. So that case is very interesting. Okay. So this is not how like Markoff or Painlevé. Well, actually, this is more or less how Markoff thought about it. This is not how Painlevé thought about it. So let me explain how Painlevé actually thought about this question. Maybe how Schlesinger thought about this question. So that would be, I guess, well, we've made it to 1860 or something. So Well, now let's get to how Schlesinger was working on this kind of thing in 1912. So this is my third attempt at an introduction. I want to explain this question from the point of view of analysis. Great. So now here we were studying S2 minus some points. Let's put a complex structure on that. So let's study representations of the fundamental group of CP1 minus some points. I mean, of course, topologically, this is just S2 minus some points. Let's suppose we have a representation, the SLRC. Well, this is essentially the same thing by the Riemann-Hilbert correspondence. As an ordinary differential equation. Okay, so let me explain what I mean by that. So this is essentially the same thing as an ODE, a linear ODE, the form some vector functions, and you want their derivative to be to satisfy some equation. So it should look as follows: bi over z minus xi f, where here the bi are traceless, are by our matrices. Okay, so what do I mean by these are the same? So they're not actually quite the same. So it's really it depends on a choice of logarithm of the AIs from before. Up to that, it should be the same. So maybe I can tell you how to go from an ODE to a representation. Well, what do? You write down a local solution, a basis of local solutions. You can always do that, and you can analytically continue them around these punctures. And that gives you a new basis of local solutions. Okay, so what does that tell you? It tells you that I1 of the space acts on the space of local solutions. So that's a representation. Okay. And up to some minor issues of Hilbert's 21st problem. Any representation like this comes from such an ODE. By the way, this Hilbert's 21st problem was supposedly solved by Plumage in 1905, and nobody caught the error until Bollebrook in like 1980 something. So it's really kind of an amazing story. Okay, but nonetheless, one can make sense of the sequence. Okay, so in terms of these ODE, how does one understand the dynamics of this situation? Well, now there's some kind of continuous thing one can do. One can take these xi and move them around, right? So what happens when you do that? Well, the top part of this diagram, the representation doesn't change. Like moving these xi changes the complex structure here, but nothing topologically is happening. On the other hand, you have to change this ODE, right? This ODE has poles at the xi. So if you move the xi, but leave the bi the same, probably we'll get a completely different representation. So isomonodromy. What does this mean? The same monodromy asks the question, which is how should you change the bi as you change the xi while keeping this representation the same? So as one varies xi, how to change bi while fixing the representation rho. Okay. And this question was more or less answered by Schlesinger in 1912. So he wrote down the differential equation that bi have to satisfy as you vary the xi. So let me write it down. So maybe let me make an assumption that the sum of the bi is 0. So this assumption is just that there's no pole of infinity. So in that case, the equation becomes the following. It becomes dbi dxj, this is for j not equal to I, should be the following. It's the commutator of bi with bj divided by xi minus xj. And then what about when I equals j? Well, you can just impose the condition that the dbi dxj is, again, there's no pole at infinity. Okay, so this is the Schlesinger equation. Okay, and the maybe the most famous example of this is that if n is 4, if you have 4 points and r is 2, this is the Painlevé 6 equation. So if you go on Wikipedia and look up the Painlevé 6 equation, you'll find a quite different looking equation, but it's this under some change of coordinates. Okay, and what's our question? So what is this question of analyzing the dynamics of the finite orbits? It's the following question. So it's, what are the algebraic solutions? For this differential equation. Okay.
Sorry, what are you summing over in that second?
Summing over J. Sorry, summing over I. Sorry about that. Yes, summing over I. Yes. It's just you want this to stay true. Right. Okay, so the question is, what are the algebraic solutions to this differential equation? And I really think this, I mean, this is really something Painlevé was thinking about. So if you go back to Painlevé's Stockholm lectures from, I don't know, about the same time Schlesinger was working on this, the early 1910s, I think. So Painlevé makes the following assertion. So Painlevé asserts something like, I'm not going to try to quote him, it was in French, which wouldn't be a problem for you, but it's maybe an issue, more of an issue for me. He claims something like the generic solution to, well, his Painlevé 6 equation, that this equation cannot be written in terms of classical functions. Okay, so he doesn't really precisely define what he means by classical functions, and the proof he gives of this is like not rigorous by modern standards, but this was made rigorous by Umemura, the 80s. I think Umemura is very generous and sort of says that his proof follows Painlevé's idea. I think there were really quite a lot was needed to do this. This is kind of the beginning of some differential Galois theory. Okay, but already Painlevé was writing down special parameters, so the non-generic case where there were algebraic solutions. Okay, and so I think sort of the inverse of this question is when are these solutions algebraic? Okay. So the fact here is that an algebraic solution is essentially the same thing as a finite orbit of this section. Mod zero n action on this section. Any questions about this? Okay, so now let me start telling you about how to classify these. So classification. Maybe I should begin by saying what's already known. Before I do that, what's the goal? It's to classify mod 0n, so finite mod 0n orbits of the action on this group on what I call x of c. Let me just write it out. It's on Hom by 1 sigma 0n at L2c of the conjugacy. So this is the goal for the rest of the talk. We want to understand the finite orbits of the section, or equivalently the algebraic solutions to this equation when these BI are 2 by 2 matrices. Okay. So we won't quite succeed, but we'll succeed, for example, if one of our matrices has infinite order. Okay, so what's next? Okay, so the first case that's sort of the case that's been the focus of most work over the last 100 or so years is the place where n is 4. So this is the case that Painlevé was originally considering. So in this case, I think the first algebraic solutions were written down by Painlevé and Fuchs and Picard at the very beginning of the 20th century. And then I think this problem was picked up by Hitchin in the late 80s and early 90s, who found actually the same solutions that Fuchs did via a different method. And then there was a huge flurry of work, notably by Dubrovin and Matsako, who you can look at their Inventiones paper where they write down like a 3-page long algebraic solution to this equation. It's actually amazing. Bolch, who found many Any other solutions? Kitaya, Duran, and maybe I won't try to give the complete list. But ultimately, this problem was finished by Lusovi and Ticky in 2014. And the nature of what they did is they showed that the list of solutions other people had found was complete. So maybe let me just say a word about it. So this was computer aided. So it's not at all obvious that this is a finite computation, but they figured out how to reduce it to a finite computation in this n=4 case. And then they showed that the list other people had found was complete. And what's the nature of the classification? There's 4 continuous families of solutions. 1 infinite countable family, infinitely infinite family, which is very closely related to recent work of Kong as well, which maybe you'll talk about next week here, I think. I don't know. Yeah, or at least you talked about it in Toronto earlier this week. And then there's 45 exceptional finite orbits. So the upshot is it's a bit complicated. Okay, then what about n at least 5? So in this case, very little is known. So what was known? So basically, there's some sporadic examples found by Ticky, Caligaris, Masato, Lorey, Yara.
I have a question. Yeah, all these kind of solutions are motivated.
So the ones with quasi-uniform and local monotropy are. Yeah, but in the continuous families, of course, not all of them. Any other questions about this? Yeah, but I should say that follows from the classification. It's not a priori obvious.
For some reason why n=3 is being ignored.
n=3 is boring because the braid group action is trivial. I one of a point. M03 is a point, right? I one of the moduli space. It's fine. Any 3 points on P1 are the same as each other, right? Yeah, so M04 is a 3-punctured sphere. M is the moduli space, right, of points on a sphere. Oh, maybe we can discuss it after. But the upshot is that when n is 3, but and r here is 2, so all the local systems are fine. All the representations are fine. And there it's exactly the hypergeometric local system. So they're still completely understood. Okay. So that was what was known. At least as far as I know. Are there any other questions about this? Okay. So let's drill down a little bit more. So we have some representation, I1 of sigma 0 n into SL2C. And let's try to analyze it in terms of the Zariski closure of its image. So let's analyze the Zariski closure of image. Well, it's contained in some maximal Zariski closed subgroup of SL2C, and we know what those are. So the first case is where this is finite. In other words, the image of this representation is a finite group. Okay, in this case, the orbit is always finite. Like if you start playing around with a representation with a finite image, you'll only get representations of the finite image. So the orbit is always finite. Okay, and the possibilities, okay, what are the finite subgroups of SL2C? So this was more or less done by like Schwartz and Klein in the 19th century. So the images are going to be like subgroups of a cyclic group, a binary dihedral group, or the binary tetrahedral octahedral. Right, those groups. So these are the maximal finite subgroups of SL2C. think, more or less. And SL2C is up to same as SO3, so this is like the same as classifying platonic solids. Okay, so that's sort of the least interesting case. Okay, so there's two other maximal proper Zariski closed subgroups of SL2C. So the first one is this one. These are the non-irreducible representations. And this here actually the classification is pretty hard, but so the classification of finite orbits was done by Cousin and Musar, and then in some sense McMullen had a different approach, although I think McMullen didn't think about it this way. He has this very nice paper, braid groups in Hodge theory, where he's essentially doing the same thing. Okay, so that's one case, and then the other case is the sort of infinite dihedral group. It's the subgroup of SL2C, which looks like this. And here the classification was done by Dickey. It's not too complicated. I won't go into it. Okay, so it only remains to classify the Zariski dense representation. What remains is the row SL2C with Zariski dense solution. Okay, so I mean, of course, you could ask, like, are there any, right? And it's not totally obvious. Like it's not that easy to write down a Zariski dense representation with finite orbit under this big group. Right? Okay, but it turns out there are actually a lot. So let me explain one way to make some. Way to make some of these is pullback. So if you have, for example, a representation like this one with n is 3, you can try to take some algebraic map from sigma 0n to sigma 0,3 and pull your representation back through that map. And if you rig your map appropriately, then you can arrange. So you can arrange that it still has finite orbits. So for example, you can pull back from sigma 0 n prime for some n prime less than. Okay, so let me explain what I mean by this. So in particular, how to rig your algebraic map to make this work. Okay, so suppose you're in the following setting, that there exists some function which depends on the xn. So it's a function from p1 to p1, which is algebraic. It's the function of the xi. And it satisfies the following properties. So first of all, such that for all I, when you plug in xi to this function, you get 0, 1, or infinity. Okay, and second of all other preimages of 0, 1, and infinity are ramified, so they have ramification order. Divisible by some fixed number, so let's say by n0, n1, and infinity. Okay, so what am I doing here? I'm rigging the situation so that if I start with a local system on this target, which has local monotomy of order like n0 at 0, n1 at 1, and infinity at infinity, and I pull it back through this map, it will only have non-trivial monotomy at the xi's. And moreover, since I want this function to exist for all xi, I get a finite orbit, so I get something that lives over the whole moduli space. So maybe let me just draw a quick picture quickly. So here's the picture. like 0, 1, and infinity, and then we give some sheets of the cover. So maybe this is x1, x2, x3, x4, and then I want all the other preimages to be of these points to be ramified. Okay. So in particular, if I take some representation of the fundamental group of this space, which is like is order 2 here, when I pull it back, it will have order 0 up here. So I'll only get maybe I should make this an x5 and an x6. But I only get non-trivial monodromy of my Markoffs. Okay. So these are called the pullback families. And so these were classified by Diarra in 2013. Okay, so is that everything? So no, it's not everything. It's still more. Okay, so what's left? So let me now state the theorem. So this is like everything in the top. This is joint with Josh Lam and Aaron Landesman. So what's our setup? So suppose representation, this group, so n matrices which multiply to the identity. Finite orbit under mod 0n. So one of these algebraic solutions to the Schlesinger equations. And let's suppose it's well, I want to say it's Zariski dense. That's the only interesting case left, but let me say that in a slightly funny way. So suppose it's irreducible. And what's a good way to make sure it's Zariski dense? So I want to require that the local monodromy around some point has infinite order. Okay, then one of two things happens. So first of all, either one, rho is a pullback. So meaning it's made via this construction, which were already classified by Diarra. Or maybe I should go to this board. I'm going to write some kind of complicated thing and then spend the rest of the talk telling you what it means. Or two, rho is MC chi of U tensor L. Okay, so what do all these symbols mean? So what does this mean? So MC chi is middle convolution. With parameter chi. And so this is what showed up in the very beginning of the talk in Katz's work on retrieval system. So I'll say what it means. It's if you read Katz, it feels very scary, but it's actually this is a totally computable thing. My student Amal Yinkal just implemented it on a computer. So it's really a very computable thing. So here L here is a rank 1 local system. So here L is a representation from pi 1 sigma 0 and C star. So again, a sort of simple thing. And then I have to tell you what this U is. What is U? So this is a representation of pi 1 of sigma 0 n into GL n prime C. So GL r prime C. So it's not a 2-dimensional representation typically, quite large dimension, which has image a finite complex reflection. And maybe let me just say, what is this R prime? So this R prime is it's n minus 2 if all local monodromies rho are non-scalar. Up to just tensoring by character, you just think R prime is always n minus 2. So this is some typically pretty large thing.
They're all coming from the geometry.
Yeah, so in particular, this shows they all come from geometries.
How about for the first case?
So in the first case, it follows from Diarra's classification that if this quasi-unipotent local monodromy, they come from geometry. They're pullbacks of hypergeometric processes.
Go back, but it's not necessary to be geometry.
Well, they're pullbacks of hypergeometric things, so they're from geometry.
3 points.
Yeah. So, okay. Great. Okay. So what is a finite complex reflection group? So I think that's I have to in the rest for the rest of the talk I want to explain what is middle convolution, what is a finite complex reflection group. I think that's what I owe you. So maybe let me first explain this. It's the simpler one. So first of all, an R by R matrix is a pseudo reflection. If the rank A minus the identity is 1. If it fixes a hyperplane. Think of reflection, for example, is a good example of a pseudo reflection. And then a subgroup of GLRC is a finite complex reflection group. If it is finite and generated by pseudo reflections. So, for example, think the symmetry group conjugacy, that's the kind of thing. Okay, so in what sense is this a classification, right? So I've reduced it to something about this. Okay, so the remark is that these finite complex reflection groups, maybe let me write it, FCRGs, were classified by Shepard and Todd in the 50s, 1954. So this was some kind of extension of Coxeter's work on finite real reflection groups.
Quotient.
Yeah, that's right. Yeah, they correspond to hyperplane arrangements, where the corresponding quotient is Smith. That's right. Yeah. Okay, so this is really a classification. Maybe let me just say a little bit more about what the classification of FCRGs looks like. How am I doing on time?
10 minutes.
10 minutes. Okay. Okay. So what does the classification look like? So there's one infinite family. So it's called GMPN. So these are very simple. These are, you take, maybe if P is 1, what they are is you take a permutation matrix, and instead of ones, you put in m-third subunity. The P means you require those m-third subunity to multiply to a P through unity or something. Okay, and then 2, there's 34 exceptional cases. And just think, let's give you a flavor. You can think odd of the icosahedron, odd of the 600 cell, some 4-dimensional regular polytope, and make the Weil group of E8. There's an explicit list of 34 of them. You can look them up on Wikipedia, which I've done many times over the course of this project. Okay. So what's the upshot? So modulo me telling you what middle convolution is, these exceptional finite orbits, the ones we didn't understand, are in bijection with, well, n-tuples of elements of finite complex reflection groups satisfying some conditions. So maybe let me just make that really explicit. So the upshot is that exceptional finite orbits are in bijection via middle convolution. With n-tuples of pseudo reflections. So really, I'm stating a slightly stronger form of what I wrote here. So this U can't be arbitrary; it has to have some specified local monotropy condition. So it's n-tuples of pseudo reflections, which 1 generate a finite complex reflection group, and 2 multiply to a scalar. to a non-identity scalar matrix. For the experts in the room, that scalar is this parameter pi. Okay, and maybe let me just remark, like, in some sense, the classification isn't complete. So you still have to go through all the finite complex reflection groups and find all the n-tuples of pseudo reflections to this property. And my student Amal is currently doing that with a computer search. It's actually not an easy thing to do. I mean, some of these pseudo reflection groups have like 600 million elements. So. So in some sense, this is a classification, but there's still a bit left to do. All right, so let me just finish up by saying where this comes from. So like, what is middle convolution, and how could you possibly prove a theorem like this? So like, how could you prove this is getting everything? Okay, so 3. What is middle convolution? So the slogan is it's to say something is the middle convolution of something else is to say that it shows up inside of the cohomology of a family of curves. Some very special family of curves. So let me give you a formal definition. Let me take X to be P1 minus some points where infinity is contained in D. So now I'm going to make some very large diagram. I'm going to take X cross X minus the diagonal. This maps to X via the projection onto the first factor. Includes into P1 cross X. This maps to X via projection onto the second factor. Okay, and then there's one more relevant map. So this is P1, well, it's a subset of P1 minus infinity in the diagonal. So I can make a map to C minus the origin, which sends XY to X minus Y. So this is well defined because I deleted the place where X equals Y and I deleted infinity. Okay, so this is middle convolution. So MC chi of U is the following. It's R1 pi 2 lower star of J lower star of pi 1 upper star of U tensored with alpha star of chi, where here chi is a rank 1 local system on C minus the origin. So in other words, a number. Okay, so this is kind of a crazy definition. This is what it is. But okay, what's the upshot? If U has finite monodromy, this is very simple.
The middle map, or
oh yeah, this is alpha. Sorry, yeah. So okay, well, this kind of crazy definition is actually pretty concrete. So if you and chi have finite monodromy, you can compute this by taking some finite cover of the space and then taking some isotypic component of its cohomology. So what does this J do? This J lower star tells you to compactify. Okay, so what you're doing is you're taking so in other words, this is the cohomology of a family of curves, the family of G cross Z mod AZ covers of P1 branched at D and some other point. So the fiber over X is branched at D and X. It's really not so scary. Okay, finally, maybe let me just finish. I think I have about 1 minute left. So let me just finish up by saying how you use middle convolution. So how do you actually prove this classification? So that this relies on the main idea is to use work with Corlett-Simpson. Which shows that well, you can interpret it as saying either rho is a pullback, or rho underlies an okay variation of Hodge structure where for K some number field. Okay, and maybe I should remark that Hangzhou has so this is something about two-dimensional representations. Hangzhou has generalized this to the higher dimensional setting under some conditions. Okay, so what does that give us? It gives us some Hodge theory to work with. So in other words, we want to analyze what this middle convolution does to the sorts of Hodge structures. And the observation I'm making this, I mean, this sort of real computation here is that you can choose L and chi such that, well, here I'm saying that rho is the middle convolution of something, but I'm instead I mentioned at the very beginning of the talk that middle convolution is kind of invertible. So I can find U by applying some middle convolution to this, right? And what I want to do is that I want to arrange that MC chi of rho tensor L has the following property: all of its Galois conjugates.
Daniel. Rho is even more. It's in second case, this is coming from the geometry origin.
That's right. Yeah. So it's a very special kind of book. It comes from maybe comes from a L2 type covariant variety. But this is all we use. Okay. Okay. So the point is that we make these choices so that this has all of its Galois conjugates unitary. Okay, so this is kind of the fact that one can do this is not so obvious. Okay, but now if you have a representation into GLN OK, well, OK is kind of discrete, and the unitary group is compact. A representation with discrete compact image has finite image. This implies this has finite image. Okay, and now you analyze what happens to the local monotomy to see that in fact the image has to be a finite complex reflection group. And it's generated by local monotomy, and all of those local monotomy matrices are pseudo reflections. Okay, and now you win because middle convolution is invertible. You just undo this. That's improved. Any questions?
So okay, so you get this kind of local system rho, okay, but then you can write down the weighted Higgs bundle for rho, right? And you have I guess in this case the Higgs field has most cases has only 1 0.
So if you have 4 points, I think
4 points. I mean,
it will usually
I mean
that's not, I think that's not quite true in general. So
not general.
yeah, I think that's not true in general. So what'll happen is, right, so what's even with 4 points actually. So let's just like stare at what this vector bundle looks like. So you have this flat vector bundle E nabla, which corresponds to some SL2 local system.
Yes.
Right. So the degree of E is typically going to be E minus 4 actually, right? Because so unless you have a lot of unipotent local monotomy, because you is if all 4 points are not unipotent. But I think typically it'll look like O of minus 2 plus O of minus
minus 1, I guess. This is for example. Yeah, 3 point. First 3 point is a unipotent. The last one is quasi.
Yeah, so in that case it'll be O
minus 1. Right?
That's right. So if 3 of the 4 points are unipotent, then it'll be O plus O minus 1, and then in this case with 4 points you'll get 1 vanishing Higgs field, but already with five points you'll have two points with the Higgs field vanishes. And there are actually examples with 5 points where 4 of the monotomies are unipotent, the fifth one is not. Yeah, so it's sort of, yeah, so the case where many of them are unipotent is very interesting, and maybe I should say Khan has studied it from a sort of very different point of view. And yeah, so then actually I think there's quite a bit left to understand with like what do the Higgs bundles corresponding to these things look like. So other questions? Yeah.
Use some property of these groups, or do you just
oh yeah, so
the list?
yeah, let me say something really kind of fun about this. So okay, so here's something you can prove. Here's a just a fact about this that I only know how to prove by using this and then going through the classification and finding. So here's a corollary. So rho as before. So let's say irreducible with rho of gamma I of infinite order for some I. This is the case you understand. Then at most n minus 6 of the rho of gamma I are sorry, at most 6 of the rho of gamma I are non-scalar matrices. So in other words, for any one of these finite orbits, you can always tensor with a character to make it have to make it only have interesting monotomy at 6 points. And that's sharp actually. There are examples with 6 points. So the only way I know how to prove this is you use this theorem to get a statement about finite complex reflection groups, and then you just go through the infinite complex reflection groups and the exceptional ones of sufficiently large rank, and show that you just go through the list. You really can use it, and of course this is working with this is an infinite family, so you have to use some properties of those that infinite collection of groups. So this is I think it's sort of a maybe this was a conjecture. I should mention this was conjectured by Tinky.
Is the corollary some sort of generalization of the pullback mechanism?
Yeah, so it's related. I'm so right. So you have to check both types of families, right? So you have to check that there's no pullbacks with more than 6 points, but that just follows from Jarrah's classification. So it's related to that, and then you have to check this other kind of construction too. So yeah, you have to use. I'm not sure if that was your question.
Well, I just sort of it has a similar flavor. Was all I'm saying. There's some bits of. So.
Yeah, I think it's sort of interesting that 6 is what shows up actually in both. Like sort of 6 is sharp for both ways of producing. Yeah. Maybe I should mention that those two constructions are not really mutually exclusive. So many of the pullback constructions also can be produced this way. Sort of funny feature of the classification.
Okay, well, let's thank the speaker again.
May can I ask questions, please?
Oh,
sorry.
Where's your voice coming from?
Because that you are in the center, he would hear you from here.
Okay, sorry. Go ahead.
And I see the first blackboard, so in case you might want to use that. First of all, thank you so much for such a great and beautiful talk. It was very interesting. A bunch of questions. Well, actually two. So first is this so is the counting problem well defined, that you fix an n and an r, and you fix a number, say that and you want to count all the finite orbits with the length less than the third number given?
Yeah, so that would be understanding that question would be a finite computation if you fix the size of the orbit. And that would be a finite computation, and I think the answer is known in the case n is 4. Like in some sense, you can open up Lisovi and Tinky's paper, and they have beautiful pictures of all the orbits. In the case n bigger than 4, I guess in principle you could count using our classification, but it would be kind of a pain. Like you'd have to. Magma has all the finite complex reflection groups, and I think you could program such a count. I guess my student Amal is doing something a bit similar, but
that sounds.
It would be a large. It's a well-defined and quite large computation.
I see. So well, in physics, what you're interested in is the asymptotics or the growth rate of these closed orbits, basically. So, and I guess, I mean, for that you can. I'm guessing that you can also find a formula for the asymptotic growth of these finite orbits.
So when you say the asymptotic growth, do you mean the growth of the size of the orbit, or if you take a solution to like Painlevé 6, like how is it blowing up?
No, so we're in our previous problem where we fix a number and we ask for all the finite orbits less than that number, and then you let that number go to infinity.
Oh, I see. That's an interesting question. I mean, I think somehow what our results are saying is that outside of the case n is 4. So right, so there's not a lot of finite complex reflection groups, right? So somehow outside of the case n is 4, 5, and 6, they're just the asymptotics there just aren't going to be anything new, which that's what this corollary is saying. And then in the case 4, 5, and 6, there could be something interesting. But I think, for example, in the case n is 4, so where you have 4 points, basically the only once the orbit gets sufficiently large, you're only going to see things coming from this infinite discrete family that I mentioned at the beginning of the talk. So these are called the Cayley solutions. So it's basically going to be like counting. It'll be counting something like 4 reflections in a dihedral group as the size of the dihedral group gets bigger or something like that.
I see. So those are the only things that contribute to large orbits.
I think that's right. And then there's sort of similar constructions coming from these GMPNs for 5 and 6 points.
I see. Great. And so just another comment. Well, what physicists love to do is quantize the space of representations or the character variety.
Mhm.
And for that, basically what you want is a Hilbert space associated with this variety
It's like
with an
these
action of.
scaling modules or.
So the best way to understand it is, at least in the case of SUN, there is a line bundle on this moduli space or on this character variety. That's called the Chern-Simons line bundle. It's a little difficult to explain, but anyways, it's a natural line bundle, and you look at sections of that line bundle.
This is like conformal blocks, I guess.
Yeah, it's going. Yes, absolutely, it's going towards that. So yes, so then I mean, so if you have such a Hilbert, so suppose your variety has a line bundle, and the mapping class group action lifts to an action of the line bundle.
Yeah.
So it acts on the sections of that line bundle.
Mm-hmm.
Can somehow one translate this problem of finding finite orbits into, let's say, the representation theory of the mapping class group on this Hilbert space?
Yeah, that's a good question. So right, so you can ask this in the analogous question for like you know, R bigger than 2, right? So higher rank representations, and also for higher genus surfaces. And there, I basically know it's basically the question of analyzing representations of like the mapping class group of a surface with marked points. So it really is very closely related. So I basically know 2 constructions. So one is some kind of Kadari-Parshin trick, where you find your representations in the cohomology of a family of covers, and so our result shows that handles everything in rank 2, basically. In higher rank, there's another construction which is to use TQ of T, and so this conformal blocks are an example of that.
Yes.
So of course there's a question which is like we don't know if that's redundant. Like it could be that every conformal blocks representation can be written in the cohomology of a family of covers, and there's some like recent results on this, like Dudillo, Yangha, and other people. So it's yeah. So yeah, you can use TQ of T to make examples of these things in higher rank, but I don't know if you need it. Maybe is one way to say.
I see. Yeah, no, I just wanted to convert it to a linear question, basically, about representations on.
Yeah, it's basically understanding the representations theory of finite index subgroups of the mapping class group. It's sort of the same question.
A finite index subgroups, I see. Okay, thank you. Actually, I mean, we can talk later because I can't see anyone, but I don't want to make people wait.
Oh, but where am I? I'm here. Okay. All right.
Yeah, that.
Any other questions?